You have become a bit more familiar with the various types of PV systems and the different components in a PV system. It is now time to look into the PV system design process. Whether you want to match the power consumption of your domestic loads or you want to optimize a PV system for a certain location, the goal of any design process is to accurately predict the energy yield of your system. In this video, you will learn about all the different steps involved in PV system design. The performance of a PV system is strongly location dependent. The design process therefore starts with collecting meteorological data for the specific location of your PV system. Important meteorological parameters are the solar irradiance, the ambient temperature, and the wind speed. There are a number of meteorological databases available online. Some global databases provide free meteorological data, such as PV3x, Solar Database, and the NREL, National Solar Radiation Database. An accurate energy yield prediction requires more than just the local meteorological data. Each system requires a detailed landscape survey. The location can be partly shaded due to the surrounding landscape, such as trees or buildings. Shading reduces the direct irradiance incident on a PV module. In addition to the direct irradiance, the Earth's surface receives a significant amount of solar power in the form of diffuse radiation. The amount of diffuse irradiance received by a solar panel at a particular location depends on the visible portion of the sky, also called the sky view factor. Moreover, light reflected on surfaces around the PV module also contribute to the total incident irradiance. In the second week of this course, you will learn that the intensity of the light that reaches the module after being reflected by the ground is proportional to the albedo coefficient of the ground surface. A PV system is not as such without some PV modules. There are different PV technologies available on the market, such as mono and polycrystalline silicon PV modules, thin film PV modules, and even flexible PV modules. The PV modules come in different shapes and sizes. Each PV module has different electrical properties, such as open circuit voltage, short circuit current, and peak power. The modules can be connected in various ways to form a PV array. The manner in which the modules are interconnected determines the output voltage and current of the array. The meteorological data and the surrounding landscape all influence the incidence irradiance on a module of a certain shape and size. In order to estimate the irradiance incident on a module at any given time, we also need to consider the tilt and orientation of the module. The incident solar irradiance on a PV array is also known as the plane of the array irradiance. The plane of the array irradiance is a combination of direct, diffuse, and ground irradiance. The plane of array irradiance varies throughout the day due to the movement of the sun in the sky. By estimating the plane of array irradiance for a given module tilt, angle, and orientation, we can find the optimal tilt and orientation for a PV system in any location. The power output of a PV module does not only depend on the incident irradiance. The temperature of the modules play an important role too. The module's temperature can be estimated by a fluidodynamic model. Such a model is based on a detailed energy balance between the PV module itself and the surrounding environment. The model takes into account the mounting configuration of the PV modules, the temperature dependence of the specific PV technology, the irradiance incident on the module, and the meteorological data such as the wind speed and the ambient temperature. At this point, in the PV system design, we can accurately predict the DC power output of the modules. However, as we saw in the previous video, the PV system consists of more than only modules. The balance of system components, such as charge controllers and inverters, introduce additional losses and limitations that have to be considered during the PV system design. Finally, we can accurately estimate the energy yield of a PV system. The power output of the system can be calculated by taking into account the DC power output of the modules, the performance of the balance of system components, and the modal shading of modules in a PV system. With an accurate yield estimation, we can determine the correct size of PV system and the energy storage component. The correct system or battery size might, for example, depend on the power consumption of the connected loads. This overview shows all the steps involved in the design of a PV system. Each week we will focus on a different part of the design process. By the end of this course, you will be able to design your own PV system for any location. Enjoy and good luck!